Okay, shall we start? So, are there any questions from last time? I'm somewhat torn between what I want to talk about and what everybody's asking me to talk about. So I'm thinking of just doing a bad job of a little bit of both. So first of all, I talked about the exact triangle, and I talked, I gave a somewhat ad hoc construction of these maps between Floer homologies. So consider the following to be a, if I had been allowed to go 10 minutes over during my last talk, I would have said the following. And then somewhere 10 minutes into my talk, we're going to switch to a different topic. So we constructed these maps by counting holomorphic triangles. Remember? So the y was specified by a Heegaard diagram, alpha 1 through alpha g, beta 1 through beta g. And similarly, y lambda of k is specified by basically the same pair, except the last beta circle was changed. So I'll call that gamma 1 up through gamma g. So the gamma i's agree with the beta I, except the last one is different. Now, so we have alphas, betas, gammas. This specifies a connected sum of g minus 1 copies of S2 cross S1. And this pair specifies y, and this pair specifies y lambda of g, y lambda of k. Now, in fact, I went through the proof of why the double composite was 0. The proof that the double composite was 0 was a count of holomorphic triangles. We had alphas, betas, gammas, and then we're counting triangles with these boundary conditions. We juxtapose those with triangles that satisfy alpha, gamma, delta boundary conditions, and show that the count of these times these is the same as the count of the number of index 0, 1 to these is the same as the index 0 count of these kinds of triangles. And then we saw that these triangles canceled in pairs. Therefore, this count was 0, and therefore this count was 0 as well. And that was, so this is not equal but homologous. Okay? Now, what I should reveal is that there's a four-dimensional interpretation of all of this. And the point is now that that this triple alpha, beta, gamma specifies as I said last time, a 4-manifold, and the 4-manifold is gotten by attaching to triangle cross sigma, alpha handle body cross an interval, a beta handle body cross an interval, and a gamma handle body cross an interval. So this is y alpha beta. This is g minus 1 copies of S1 cross S2. And this is y alpha gamma. And the count of triangles here, so we have now this map which sends a Floer homology class from the Floer homology of y alpha beta out to the triangle count alpha beta gamma of this Floer homology class tensored with the canonical top dimensional generator of S1 cross S2. I guess we're working in the hat theory. But this map is what we define to be the map associated to this two-handle addition. So a framed knot in a 3-manifold specifies a two-handle addition, and we define, so we had our y, and we formed y lambda of k. there's a canonical four-manifold now that bounds that, which is gotten by a single two-handle addition, and let's call that W lambda of k. And we define this to be FW lambda of k. And let's just do a simple example. Let's just redo a simple example we did over here. What happens if we consider I'm just going to relabel things now. So if we go from S3 to S3, suppose, how should we call these things? We want to call it, let's say this is alpha, beta, and gamma. So the cobordism that I'm specifying here now belongs to the unknot with framing -1. So this cobordism corresponds to CP2. And the other point I should make is that in general, this cobordism, I say, we count all holomorphic triangles. But the space of holomorphic triangles decomposes again much the same way that the space of homotopy classes of paths decomposes into as follows. If I have so suppose, let's go back to this picture here. The claim is that FW decomposes into FWS, where S is this is the set of spin C structures on W. And the way this works is that the space, if we're counting holomorphic triangles here, the space of holomorphic triangles that connect pi2 x, y of W, this, just like the space of periodic domains was isomorphic to the two-dimensional homology of a three-manifold plus Z, this is isomorphic to Z plus, and now the two-dimensional homology of this four-manifold. And how do we see that? If I take one triangle that connects the same 3 points, so I've got a triangle whose boundaries live on the alpha circles, the beta circles, and the gamma circles, and I, let's say, juxtapose onto that a different triangle. So if I take the difference of two triangles, then I get what you might think of as a triply periodic domain. It's a homology between the alpha circles, the beta circles, and the gamma circles. Now, a homology between the alpha circles, the beta and the circles, and the gamma circles can be thought of, remember this is sigma cross a triangle. That can be thought of as a homology supported in the interior here whose boundaries are in the alpha circles, beta circles, and gamma circles. Well, I can complete those off in the three handle bodies. And in that way, I construct a closed surface in this four-manifold. So you see now that the space pi2 x, y, w, where x, y, and w are fixed, is isomorphic to two-dimensional homology of x with z coefficients. And now we say that two homotopy classes, psi and psi prime, are spin C equivalent if, where psi here is in pi2 of x, y, w, and psi prime is in x prime, y prime, w prime. These are spin C equivalent if if I can juxtapose flow lines, so I've got my psi which goes between x, y, and w, and I'm going to juxtapose on a phi which goes from x to x prime, a phi 1 which goes from x to x prime, a phi 2 which goes from y to y prime, and a phi 3 which goes from w to w prime. And since that gives us a larger equivalence relation, which you can think of as we're taking the space of triply periodic domains and allowing to act on it by the space of doubly periodic domains. So that's like taking the two-dimensional homology of this 4-manifold and looking at its orbits under the action of the two-dimensional homology of the boundary. So that is to say, the set of spin C equivalence classes of triangles triangles is isomorphic to, again, a z with this by the nz plus the two-dimensional cohomology of x. And in fact, there's a way to construct, it's an affine space for the two-dimensional cohomology, and in a way which now I would prefer not to explain, it gives you, this space can actually be mapped, this set of spin C structures on X. But the point is that, the point I want to make, well, my W has mutated into an X. But the point that I want to make is that, that homotopy classes of triangles can be naturally partitioned into equivalence relations which correspond to spin C structures. Okay. And let me state now this example that we were looking at, CP2 bar. There's this small triangle C1, and there's also a small triangle C2. Or C minus, well, this small triangle C1, there's a larger triangle C3, there's a yet larger triangle C5, and then there's another family of triangles C minus 1, C minus 3 on down. Do we see these triangles? So these, I claim that these represent the various spin C structures on CP2 bar. In fact, they're the ones whose evaluation on E, the first Chern class of C 2k plus 1 evaluated on E is equal to 2k plus 1. So, So what we have here is that the map f hat associated to psi so let's call this so well psi 2k plus 1 represents the spin C structure S2k plus 1 whose first Chern class evaluates 2k plus 1. And what we have in this language now is that pardon? Oh, E is the generator of the two-dimensional homology of CP2 bar. And I'm thinking of now CP2 bar as twice punctured. So I'm thinking about this as a map from, so this is CP2 minus 2 points. So we think of it as a map from S3 to S3. And what we have in this language now is that the map induced by the spin C structure S1 is just as a map from HF hat of S3 to HF hat of S3. This map is an isomorphism because there's a unique triangle that connects the canonical generators of all three of these three manifolds. And similarly, the spin C structure S minus 1 from HF hat of S3 to HF hat of S3 also represents an isomorphism. And all the other spin C structures give you the zero map. Maybe I should also say that all of these constructions can be made to work in the other theories. I've talked so far about the hat theory, but there's also, in the minus theory, for example, we can say that the image of xi now is going to be a sum over all sum over all w in T alpha intersect T gamma of a sum over all homotopy classes in pi 2 x theta beta gamma w of the number of points in the moduli space times w I minus nz of C. And in that way, we now have an induced map on the minus theory. And in that picture now, what is FWC3 in this example? Sorry, not hat, but minus. Do I hear any takers? So what is it if I evaluate it on the generator theta alpha beta 0? So this was alpha, this is beta. Now there's a larger triangle and it contains the reference point ones. So it's going to be theta alpha gamma minus 1. So it counts the fact that there's a single lattice point in here. So we could say this slightly more invariantly by saying that FWC3 of our generator theta is equal to U times this is the generator of HF minus of S3 is U times the generator of HF minus of S3. What about C minus 3? What? Did I hear anything? What's that? No, I'm subtracting off NZ of C. So this is U times, remember, this is U of theta alpha gamma 0 is equal to theta alpha gamma minus 1. Okay, and what about C minus 3? No, it's not plus 1. This also just contains the reference point ones. No, it doesn't wrap the other way. So this is oriented in the same way this is oriented. So it's the same. And similarly, C5 now is going to be U cubed, and C minus 5 is also U cubed. So, and so forth. So you see that, that f of W C2k plus 1 is going to be equal to multiplication by u to the k times k plus 1 over 2, or I'm off by 1. So does this work? If k equals 0, this is 0. If k equals minus 1, then this is 0 as well. So this is the So let's just check it. 3k equals 1. Yeah. What's that? Pardon? This is multiplication by u. U, remember, u is all of, HF minus is a HF minus of any 3 manifold is a module over the polynomial algebra Z of u. And HF minus of S3 looks like a canonical generator, u times that canonical generator, u squared times that canonical generator, etc. So we have here is that the 2k plus first triangle, the 2k plus first spin C structure, induces multiplication by u to the k times k plus 1 over 2. Okay, so where are we going with this? This gives a nice four-dimensional interpretation of why the maps, so I had the maps induced by these cobordisms. In the exact triangle, I have the cobordism from W, I have the cobordism W from y to y lambda of k, and I have a cobordism W prime from y lambda of k to y lambda plus mu of k. And what I said was that the double composite was 0, and the reason that that was true was that there were these triangles that canceled in pairs. But one can say it sort of more invariantly by saying that if you take this double composite, it contains in it a sphere of square minus 1. And the statement is that the composite of F composed, the composite cobordism, where we take this W and glue on along y lambda of k, this other cobordism W prime, this is the same thing, so one has to prove that this cobordism induces the same map as a different way of splitting up this same cobordism so that it contains just a minus 1 sphere inside of it. But the point is that the minus 1 sphere, well, gosh, maybe that's not a nice way of saying it. But, well, the point is that on this 4-manifold, the spin C structures come in pairs. For which the maps cancel. Okay. Well, so be it. There's a long story which I'm now not going to tell, which is that these two-handle additions, in fact, can be put together to construct maps induced by arbitrary cobordisms between two 3-manifolds. And the map induced by these cobordisms is well-defined depending only on the smooth structure of W. And the final point that I need to put up on the blackboard here is that so these cobordisms can be used to construct maps belonging to arbitrary cobordisms. Let me call it FW, going from, so if W is a cobordism from Y1 to Y2, there's an induced map FW going from the Floer homology of Y1 to the Floer homology of Y2. And indeed, if you endow this cobordism with a spin C structure S, then it goes from the Floer homology of Y1 equipped with the spin C structure S restricted to Y1 to the spin C structure S restricted to Y2. And finally, if the spin C structure restricted to Yi are torsion, then the Floer homologies can be given a rational grading. So each element in the Floer homology is graded by a rational number, which is uniquely specified by the following axioms. First of all, the Floer homology of S3. So again, here I didn't specify which type of Floer homology. We can use either plus, minus infinity, or hat. And the characterizations that HF hat of S3 is supported in dimension 0. In degree 0. And the second property is that if the S restricted to Yi are torsion, sorry, did I say, what do I mean by torsion? I mean the first Chern class of the spin C structure restricted to Yi is torsion. If Si are torsion, then the grading of an element FWS of Xi minus the grading of Xi is given by this formula C1 of S squared minus 2 chi of this cobordism W minus 3 sigma of W divided by 4. So this is the formula that Andras put up on the blackboard. And the point is that there's a unique way to grade all the Floer homologies simultaneously so that this formula holds. The proof that that's true essentially amounts to the fact that it's similar to the argument that the induced maps of cobordisms is well defined, but it's somewhat easier because it's just an index calculation rather than a count of holomorphic triangles. And there's a model calculation is that it's true for CP2 bar. So that essentially you can work out from what I've said. I told you that the drop in degree, I've told you what the drop in degree, remember that for S3, the 2k plus first spin C structure is multiplication by k times k plus 1 over 2. That drops degree by k times k plus 1. And if you subtract off C1 of S squared, if you subtract off this quantity, you'll see that you get a constant that's independent of your spin C structure. So I'll leave that as an exercise. Okay, well, I've said the things I didn't want to say, and now I can start today's lecture if there are no questions. Yes?
Yeah, when you pick theta,
Mm-hmm.
you pick the one that has highest.
Yes, right.
And what was the reason for that?
That's the one that works. So, that's the one that's independent. If you stabilize your Heegaard diagram once, then now you have to use a different theta. But you want sort of one canonical theta that's true, that works for everything. So that's the reason to pick the highest. Okay. So let me talk about something completely different unless anyone else wants to ask anything else about this. Oh, right. So the point is that we're squaring the first Chern class. And we have a 4-manifold equipped with a spin C structure whose first Chern class is torsion when you restrict it to the boundaries. That when you square that, you don't get an integer, you get a rational number. Okay. Maybe next lecture I'll give some applications of this. So this is a useful fact when you look at the exact triangle.
And just a really stupid question. And then you can figure out what degree 0 is for anything by using the cobordism, which is, I mean, just using something with the taxon.
So that's right. That's how you define the spins for anything. Degree 0 doesn't necessarily make sense, but the degree of anything you get by just kept going back to S3 and evaluating this kind of quantity. That's right. Okay. So let me now switch gears completely and talk about something entirely different, unless there are any objections. So the thing I'd like to talk about now is not Floer homology. And this is the kind of structure that, so a lot of what we had seen so far in Floer homology was, at least one saw bits of it in its sort of gauge theoretic ancestral home. But not Floer homology is something which seems to be quite new, doesn't belong to well, it wasn't predicted by gauge theory, so to speak. But knot Floer homology is a theory which is associated to a knot in a three-manifold. It's useful to think of K as a null homologous knot, and in fact, for the purposes of today's discussion, let's have that three-manifold be S3. We're going to be forced to talk about S1 cross S2 soon, but let's just let it be S3 for the moment. And the basic construction starts from a Heegaard diagram for S3, which is compatible with the knot. So let me just draw up a Heegaard diagram. In fact, why don't I draw the Heegaard diagram that Zoltan drew for S3? Okay. Well, let me draw it. Give this pardon. So let me just draw it. So let's call this beta 1, beta 2, beta 3, beta 4. Let's call this alpha 1, alpha 2, alpha 3, alpha 4. And I'm going to call the base point now W rather than Z. So here's a Heegaard diagram for S3. Now, okay, Floer homology is sort of simple. But what happens if we have not one but two base points? So we've so far always talked about Heegaard diagrams with a single choice of base point. And I'm now going to call that base point W rather than Z. But what happens if you have not one but two base points, W and Z? What does that belong to? Well, that belongs in a natural way to a knot embedded in the three-manifold. So if I've got W here and I've got Z here, then I have a pair of flows that I can glue together, and that way I get a knot in the three-manifold. Another way of thinking about this is if I've got not a single point out in the complement of the betas and the W's, suppose I have a point that's sitting right on top of one of the betas. Then I can resolve it into a pair of points, W and Z, which live on either side of that distinguished circle. And the statement is that the knot, the meridian for that knot is precisely the knot that you get by connecting up the W and the Z. So let me just say this neatly again. So a Heegaard diagram is compatible with A naught K if beta 1 is a meridian for k, and k lives inside of the beta handlebodies. And given any knot, you can find such a Heegaard diagram. We talked about that last time. And now, if given a knot, given a Heegaard diagram compatible with a knot, we can choose two base points, one on either side of beta 1. So in this case, I picked W and Z. What does this give us? So we can look at the hat complex, where we say that the differential of x is now going to be a sum over all y and T alpha intersect T beta over a sum over all homotopy classes in pi 2 xy with NW equals 0. I apologize for the change in notation. I changed from W's to Z's. So this is the chain complex for S3 using this reference point W. What does the reference point Z give us? Well, the claim is that the additional reference point Z gives a filtration of this complex, which is defined by saying that the filtration level of any intersection point x minus the filtration level of any intersection point y is equal to nz of phi minus nw of phi. Why is this a filtration? Well, this is a filtration because if y appears in the... what does a filtration mean? A filtration means that is a function from a generating set into the integers, the generating set of a chain complex into integers with the property that if y appears in the differential of x, then that function on y is smaller than or equal to that function on x. And why is this a filtration? Because if y appears in the boundary of x, then nw of phi is 0, and nz of phi is always non-negative because phi has a holomorphic representative. So this is a filtration. And we can look at and the theorem is that the filtered chain homotopy of this complex is an invariant of K. I should mention that this theorem is, again, of course, joint work with Zoltan, but it was independently also constructed by Jake Rasmussen in his thesis. And I'm going to list properties of this knot Floer homology, some of which have also been independently discovered by Jake. So there's a neat way of, so a filtered chain homotopy type of a chain complex is not necessarily an easy object to study, but you can look at the homology of the associated graded object. And to say that very concretely, we can look at what you might call CF hat K of Ki, which is going to be the free abelian group generated by those T alpha intersect T betas for which the filtration level of X is equal to I. And now the differential of X is going to count Y and T alpha intersect T beta. It's going to count homotopy classes phi and pi 2 xy with the property that nw phi equals nz of phi equals 0. And then we count the number of holomorphic representatives of phi on R times y. So this now is a chain complex which splits according to the integers. Yes? Sorry, say again? Oh, now nobody can see. It's too bad. Is this visible? So that is to say, we're counting the same differential here. You just add this condition that nz of phi equals 0. And we look at those, the generators are those intersection points whose filtration level is I. Now, there's a slight white lie which I have, which is that I've only defined the filtration level difference. So incidentally, notice that this filtration difference depends only on x and y. Oh, I didn't say what phi was. Phi here is any homotopy class which connects x and y. But this quantity on the right doesn't depend on the choice of homotopy class, because any two homotopy classes differ by the addition of a sphere, which has nz equals n phi equals 1. So this difference doesn't depend on the choice of homotopy class. It depends only on the x and the y. So there's a well-defined filtration level difference. What I didn't tell you is what the filtration level, how to lift that from a relative filtration to an absolute filtration, but maybe I can do that now by stating some. So the homology, so we can define the homology in the obvious way. And now this has various properties. And the first property is that the sum of the Euler characteristic of HF hat k I times t to the I and z, this is equal to the Alexander polynomial of k. So although I only told you how to define the difference between these two functions and didn't tell you how to give a z lift, the fact that the Euler characteristic is equal to the Alexander polynomial gives you a way of making that into a z, and gives you a z lift by requiring this to be the symmetrized Alexander polynomial. So that's the first property. Let's just do that in the case that I've drawn over here. So this is not any old Heegaard diagram for S3. It is a Heegaard diagram for S3, which is compatible with this knot that I have drawn right inside of it, which happens to be none other than, so look at this knot. So this knot runs through the beta handle body, and beta 1 is a meridian for that knot, and the knot misses all the other beta circles miss, the other attaching disks miss the knot. So this is a Heegaard diagram which is compatible with the left-handed trefoil. And let's think about how many intersection points there are. What are the generators? Well, this beta circle meets this alpha circle. This beta circle cannot meet this alpha circle, but it could meet either this or this alpha circle. Right? And this beta circle can meet either this, this, or this. And finally, this beta circle can meet this or this. So you'll see that there are actually three possibilities. Either we have that this meets this, and we have A here. If this beta circle meets this, so there, that is to say, let's just look in a little neighborhood. In a little neighborhood, we have this kind of picture. And there are four possible intersection points, which correspond, so this is, we've associated to this crossing, this picture right here, is blown up right here, corresponds to a crossing of a projection of the trefoil knot. And at each crossing, there are four quadrants corresponding to the four possible alpha circles that this beta circle can possibly meet. However, this alpha circle doesn't exist. This one is already taken by this beta 1. So we're left with either having an intersection point be here or here. So we can either have it be on the left. If it's an A, then now let's see what this beta circle can mean. Now, this beta circle can either be, the corresponding intersection point could either be here, but if it's there, then well, it could either be there, sorry, it could in principle be here, but if it's here, then there's no place for this intersection. There's no alpha circle left for this beta circle. So this beta alpha, this has to be like this, A, or B, or C. So I'll leave that as an exercise. The point here, if my explanation wasn't clear enough, the point is that there are 3 intersection points of T alpha intersect T beta. The one I labeled by AAA, the one I labeled by BBB, and the one I labeled by CCC. Okay. And what's say the filtration level difference between B and C? Well, what we have to do is we have to draw a domain that connects B and C and calculate NW of phi minus NZ of phi. Well, here's a domain that connects B and C. Do you see it? So it looks kind of like this. Okay, so it's got a little arc on this beta circle, and it has it's got a little arc on this beta circle, it's got a little arc on this beta circle, and it's got these 2 alpha arcs. Okay? You can shade it in your picture. And this domain uses the intersection point Z once. So what we see from this picture is that the filtration level of B minus the filtration level of C is equal to 1. And in fact, the filtration level of C minus the filtration level of B is equal to 1. And in fact, if you work it out, you see that there are going to be 3 generators, C, B, and A, and their filtration differences look like 1, 0, and minus 1. And this corresponds to the fact that so that is to say, the Knopfler homology in filtration level 1 is a Z, the Knopfler homology in filtration level 0 is a Z, the Knopfler homology in filtration level minus 1 is also a Z, and that corresponds to the fact that and it's of course consistent with the fact that the Alexander polynomial of Trefoil is 1. Okay, so let me give you some other properties of Knopfler homology. The second property of Knopfler homology is that the Knopfler homology of a connected sum of 2 knots is the tensor product of the Knopfler homologies of the 2 corresponding knots. The third property is, and this corresponds to the fact that the Alexander polynomial is multiplicative of the connected sum as well. The third property is that for alternating knots, yes? Yes.
Is that the only domain then? Because we still need to get you still need to get the regular Heegaard Floer homology of S3.
Yes. So it turns out that in the regular Floer homology, there's a Z that connects, there's a differential that connects C and B. Yes. Okay, that's the one I just drew. Right, and that has a holomorphic representative. Okay. The other property is that for alternating knots, in filtration level I, we get so what I should say is that I've talked about the chain complexes as splitting according to filtration levels, but there's also a degree. And the degree is induced from the Floer homology of it. So this is the associated graded object to a chain complex which calculates the homology of the 3-sphere. So the degree here comes from the fact that the Floer homology HF hat of S3 is isomorphic to Z. And we declare the degree to be in dimension 0. So since there's a differential that connects C and B, this A, which is in dimension -1, is declared to live in degree 0. And in fact, you can calculate that this lives in degree 1 and this lives in degree 2. But the statement now is that the Knopfler homology in a fixed filtration level lives in a fixed degree as well. And that degree is given by I minus the signature of the knot over 2. And the rank of the Floer homology you can calculate by just writing down the Alexander polynomial of the knot. In other words, this is a generalization of a theorem of Murasugi, which says that the coefficients of an alternating knot, the coefficients of the Alexander polynomial of an alternating knot are alternating.
I hate to make you say something again, but the numbers not in brackets are the filtration level, the numbers in brackets are...
Yeah, so I'm sorry. This is an absolute value sign, and this is just a z to the something, and the number in parentheses down here means what degree it lives in.
No, I mean, so that's what degree C, B, and A are.
Oh, yeah. So they live in degree 2, 1, and 0, respectively. This you can see by looking at the Floer homology of S. So there's a sort of slew of properties that you can write down. Of the Alexander polynomial that you can generalize. And the next property is that K is a fibered knot. Then, well, we know the Alexander polynomial is mnemonic, but in fact, the corresponding statement for knot-Floer homology is that the knot-Floer homology in filtration level G is isomorphic to Z. So somehow the Floer homology is monic as well. This is going to play a role in, I think, in Andrasch's story. But maybe the most important property of knot-Floer homology is the following, so where knot-Floer homology diverges from sort of the classical Alexander polynomial happens here. Remember, the degree of the Alexander polynomial gives a lower bound on the genus of a knot. In the same way, we can look at the maximum over all D such that the knot-Floer homology in degree D, in filtration level D, is not 0. That gives you a lower bound on the genus of the knot. But in fact, it gives you a sharp lower bound. So the knot-Floer homology actually contains the genus. And in particular, if you have a non-trivial knot, then its knot-Floer homology is non-trivial. So, for example, the result on alternating knots might make you think that knot-Floer homology is kind of uninteresting because it looks like it's a completely classical information, but the genus bound tells you that, in fact, it's not completely classical. The G in 4, yes, that's also the genus of the knot. Yeah, so it's, okay. So, let me just, yeah?
Okay, so alternating knot all differs as trivial?
Yes, because the Floer homology is all supported in a single dimension. Well, sorry, that question. In a Floer homology, of course, differentials are trivial, but in fact, you can write down a chain complex for which the differentials are trivial. So let me just conclude by saying something sort of coming as close to combinatorial as possible about this. Let me just repeat this picture up here. So given a knot projection, you can always write down an associated Heegaard diagram, which belongs to a thickening of the knot. And in fact, suppose that the knot projection is labeled with a distinguished edge. Then you can always draw a Heegaard diagram where corresponding to the distinguished edge, you introduce a meridian. Corresponding to each crossing, you attach little saddle-like beta curves that look like this. And corresponding to each of these regions, we associate alpha circles. There's a way of thinking about the intersection points here, just in this picture, as follows. The edge with the star eats two regions. How? Well, it eats two regions, and what we're going to do is we're going to associate to each vertex in the crossing here one of the four neighboring regions, with the rule that no two vertices gets associated with the same region. Okay? These objects are classical. So that is to say, given a knot projection and a distinguished edge, you can look at the set of associations which associate to each crossing one of the four neighboring regions so that no region gets counted twice. The set of such assignments is called the Kaufman state. So we have given a knot projection with a distinguished edge, a Kaufman state is an assignment x from the crossings of K to the regions of K minus the two which contain the edge, the distinguished edged E. And it's not hard to see that from the Heegaard diagram that I've drawn up there, the Kaufman states are in bijection with the intersection points of T alpha intersect T beta. And if you in fact work through, the construction of these domains, you will see that the filtration level of an intersection point X can be calculated by summing the following local quantities. So given a crossing, the crossing can look like this. Crossing in the knot projection can look like this, or it can look like this. We associate the multiplicity minus 1/2 here, plus 1/2 here, 0, 0, or plus 1/2, minus 1/2, 0, 0. And this is at each crossing of the knot. If the given Kaufman state lands in one of these four quadrants, you just add those four local multiplicities. And the statement is that the filtration level of X is equal to the sum overall of Xi's, Xv at each vertex of this local quantity, S of V, Sv of X. So, for example, we orient this knot like this. Then, according to those rules, we add up a half minus a half, a half minus a half, a half minus a half, and we see that this a half and this a half and 0. We add those up; they contribute 0. This is the state which contributes to filtration level 0. And finally, sorry, I seem to be going over a little bit. Finally, there's another local multiplicity that you can add up, which is which is minus 1, 0, 0, 0, and plus 1, 0, 0, 0. And the grading of X is calculated by, let's call this M of V. This is gotten by adding over each V in X, the MV of X. So these quantities tell you what the grading is. So that element that we just drew, you see, lives in grading 1 because, well, this generator lives in grading 1 because it's the only point that contributes. So it lives in grading 1, and there's another element in grading 2, another element in grading 0. So there's a completely combinatorial description of the chain complex generators, their grading levels, and their filtration levels, but their differentials remain elusive to calculate. So this is the status of Knot-Floer homology. I want to state a final property before I quit, and that is the analog of the Skene relation for the Alexander polynomial, which is a Skene exact sequence, which relates the Knot-Floer homology of a knot which has this kind of crossing to the Knot-Floer homology of the link, which I haven't quite defined, but I'll explain in a moment, back to the Knot-Floer homology when you change the crossing. And there's a long exact sequence like this which respects the filtration levels. And let me just say very quickly where this exact sequence comes from. It comes from the exact sequence for surgeries, where we now we perform, here's our knot K, and we have a linking unknot. And we perform either no surgery on that linking unknot, that's the first thing. We do +1 surgery on the linking unknot, that's this object right here. Or we perform 0 surgery on the linking unknot. And that is by definition the link-Floer homology. So you have to prove that what you get here, this object belongs in a natural way to this two-component link that you get by resolving the knot, that it's independent of kind of where you do this. But once you verify that's a link invariant, one proves by adapting the exact triangle proof that I gave last time in this present context to prove that there's a Skene exact sequence of this type. And in fact, once you've established this, the proof of the first property that the Euler characteristic is the Alexander polynomial is just kind of routine. Okay, well, that was 2 lectures squished into one monster, for which I apologize. But anyway, maybe I should stop. Okay.